So by now, you've seen where Monte Carlo simulation can be useful in business analytics. If we're studying stockout probabilities, inventory control, if we're studying customer behavior. So often I get students asking, where else can I apply Monte Carlo simulation? It's a cool tool to have. Where else can I apply it in my life? And one of my favorite examples to go over is applying analytics to your love life. How can you use analytics and Monte Carlo simulation to figure out who you should be married to? And so, in this example, we're going to study the perfect mate problem, trying to find the love of your life. How can we develop a strategy that, in some sense, optimizes the chance that we'll end up with the very best mate possible for us? Now, it's my opinion that there's no such thing as the one that we're supposed to go out and find. I think that there's a ton of suitable people out there in the world that we would be perfectly compatible with if we ended up married to them. So we're going to take that viewpoint and we're going to say, okay, over the course of our lifetime, we're going to run into 10, 20, however many people that ultimately you would have a successful marriage with, have a very satisfying spouse. And our goal is to try to get the best of those 20 people. So our overall strategy is going to lead our life in two overall phases. Phase one will be dating mode, where we essentially test the waters, see who is out there, to get an idea for how good or how not so great some of these compatible potential spouses would be. After dating mode ends and we have a pretty good idea of who is out there, then we switch into marry mode. And the idea is that we're going to marry the very first person who's better, more suitable, or just we like better, than anyone else that we ran into during date mode. So to get an illustration, let's actually head on over to R here. And what I'm going to do is I'm going to assume that over the course of our lifetime, we meet 15 compatible spouses. And I'm going to come up with a rating system for each one of those, each 15 of those potential spouses. And I'm going to do that just by picking a random number between 7 and 10. Let's say the scale goes from 1 to 10, but to be a compatible, suitable spouse, a minimum of a 7. So let's go ahead and generate 15 random numbers with the runif command that vary between 7 and a max of 10. So we're not privy to the sequence of ratings of people that we haven't yet met here. So all we have to go with are the ratings that we would assign individuals during, say, date mode. So for this simple illustration, let's imagine that date mode is 4 people. We're going to test the waters just by dating, getting to know 4 potential spouses, automatically dismissing them. And then the goal is that we'll send a proposal out to the first person we run into who's better than those 4 people in date mode. So let's take a look at the ratings. So person number 1 that we met scored a 7.7. Person number 2, a little bit worse at a 7.4. A little bit worse, 7.1 for the third person we meet, and then an 8.3 for the fourth person. So if date mode lasted for 4 people, we automatically break up with these 4 and move on to the next, regardless of how much we like them or not. This is our strategy. And then we switch into marry mode. So after date mode ends, we enter in marry mode and we're going to propose to the first person who's better than all of the people we saw in date mode. So the first person we meet in marry mode, we end up giving a rating of 8.0, not as good as that 4th person we ran into in marry mode. The 5th person, not as good. And then the next person, we get a 9.99. Really, really close to perfection. So we send a proposal. Of course, the potential spouse accepts. You have a fantastic wedding, and you all live happily ever after. So was that the best choice, though? So in this case, we ended up with a pretty darn good one. If we scan through the ratings of the people that we never really actually quite ran into over the course of our life, we can look to see, well, did anyone do any better than a 9.99? And in this case, no. We actually ended up with the very best possible choice. Now, if we were to run this again without setting the seed, here is who we would run into in date mode. In this case, the very best person is an 8.7 in date mode. The person we send the proposal out to is this 9.97. They accept, we live happily ever after. But was that the best choice? Well, we can scan down through the rest of these numbers, and in fact, we see that, yeah, we actually ended up with the best choice once again. Seems like a pretty good strategy. Let's try it one more time. Here are the 4 people we run into in date mode. The very best person was a 9.865. So who do we send the proposal out? Well, trying to beat a 9.865, marching down, marching down, marching down. Uh-oh. So after we ended date mode and entered marry mode, we never actually run into someone who was better than the second person that we dated. And unfortunately for us, we're terrible breakup artists, and as soon as we've broken up with someone, they never, ever, ever want to have anything to do with us again. So in this case, we never send out a proposal at all. We remain unmarried, single, alone, but at least we have analytics to keep us warm and comfortable at night. One last example here. The best person during date mode is an 8.8. Who's the first person that we end up sending that proposal to? Well, this 9.5 over here. Was that the overall best choice? No, because the very next person, who we never actually ended up meeting because we sent out the proposal to this person, and they accepted, of course, we never actually meet this person, so in this case, we end up with second best. And so that's what I would like to use Monte Carlo simulation to study. If we live our life in 2 phases, date mode and marry mode, then what are the chances that we'll end up with the overall very best choice of spouse, or second best, or third best? Or what's the probability that we end up unmarried through the rest of our life and only have analytics to keep us company at night here? So why don't we write a Monte Carlo simulation to explore this problem? Now, a little bit of terminology here. We're going to come up with a number ahead of time that represents the total number of suitable spouses that we'll run into over the course of our life. Now, this will be a guess that's personalized for you. We can represent this just as the letter M. And for some people, that might be relatively high. You might be really compatible with a lot of people. For some people, M might be relatively low. It's relatively hard for you to find a person that you're super compatible with here. So M is a number that we'll fix ahead of time for this simulation. It might vary from person to person. And then what we'll do is we'll come up with a strategy, namely, when should we stop date mode? So we're going to split date mode into the first D people that we run into. The remaining people will be the people that are in marry mode. And so starting with person D+1, we end up sending out a proposal and then marrying the very first person who's better than all the people that we ran into during date mode, or equivalently all the people that we've run into up to that point. So what's the probability of getting the overall best mate in the top 10 of best mates, etc.? Let's go ahead and explore an option here. Now, in the notes, and to be compatible with the notes, what I've done is to come up with a very specific example where M is just going to be 7 to keep things simple. So over the course of our lifetime, we would meet 7 potentially compatible mates. And I'm going to have date mode be the very first 3 of those potential spouses. We automatically break up with those 3 potential spouses and then hopefully marry the very next person that's better than those 3. So this is the number of potential spouses we'll meet over our life, and this is the number of people in date mode that we automatically dismiss. That's a nice way of saying break up with. Terribly, because they don't want nothing to do with us afterwards. So let's look at just a few examples of who we end up with, and this is also in the notes as well. I find that whenever trying to tackle a fairly complex simulation, it's useful to just think through a few potential examples and anticipate what your code should actually be returning to you. That way you know when your code's working or when it's not working. And so let's start out by considering a few scenarios. So here is some sequence of 7 potential spouses that we run into. And the difference with these numbers and the random uniform numbers that we used in the motivating example is here I've converted these into ranks. So someone's going to be the overall best match. We're going to give them a rank 1. Someone's going to be second best. We'll give them a rank 2. And so equivalently, instead of dealing with the overall ratings between 7 and 10 themselves, we can imagine just having the ranks of the individuals that we're dealing with here. So the very first person that we met in date mode is actually the 5th most suitable spouse. The second person that we met in date mode, the 3rd most suitable spouse. The third person we met in date mode, the 7th or least compatible spouse here. So after these first 3 people, we exit date mode and we say, all right, let's marry the first person we come across that's better than everyone we run into in date mode. So the very first person is actually rank 2, unbeknownst to us, better than the 3 people we ran into in date mode, so we end up marrying the person rank 2. We never actually meet the overall most compatible mate. In this example here, well, unfortunately during date mode, unbeknownst to us really, we run into and break up with the overall best compatible spouse for us. So we never run into anyone who's better than the people we dated in date mode, so we end up unmarried. Here's an example where here are the ranks in date mode here, 6, 7, and 2. We marry the very first person that's better than everyone that we run into in date mode. We actually end up with rank number 1 here. So we end up with the best of all possible choices. So our goal in writing a Monte Carlo simulation is how can we kind of develop the logic so that the computer can automatically decide and determine which of these people that we're marrying, or if we're going to end up alone. So I have some reminders up here for me that just says, hey, make sure you name these variables this way to be consistent with the notes. And so these are the names of the variables that I'm going to consider. So first off, I'm going to define a vector that represents the ranks of the potential spouses that we run into over the course of our lifetime. And so I'm going to come up with an ordering just to work through the logic first, where I know what the answer is going to be. And I'm going to have 7, 4, 3, 6, 5, 2, 1. All right, so date mode is 7, 4, 3. The first person we run into that's better than all the individuals in date mode is 2 here. So we're going to end up with the person ranked number 2. So how can I get the computer code to automatically figure that out? All right, well, what I'm going to do is I'm going to take my vector ranks, which represents the rank of the spouses that I'll eventually run into over the course of my life. I'm going to split these up into 2 different vectors, a date mode and then a marry mode vector. So date mode is just going to be the first D entries, first D elements of ranks. So I'll shoot these over so they appear in the global environment here. Let's get M and D defined as well. And marry mode is going to be the rest of them. And my shortcut for everything but a certain set of elements is to put a minus sign and then parentheses and say what elements I don't want to see. So if the first D elements are the people that are going to be in date mode, the remaining, everything but those first D, are going to be in marry mode here. So as a sanity check, print those out to the screen. 7, 4, 3 looks like it matches up. Marry mode, let's make sure it's 6, 5, 2, 1. It is, we're good. So let's go ahead and create a variable called best seen that's going to be the rank of the person who's best that we ran into during date mode. So who is going to be the best person we ran into during date mode? Well, if I ask for the minimum of date mode, that's going to be the best rank. Number 1 is best, number 2 is second best, etc. Min of date mode here is working out to be 3, which we can confirm. And so that is essentially what we're going to try to beat. When we're in marry mode, we're going to propose and marry the first person that's better than all the people that we ran into during date mode. So what we can do is define a vector called better ranks, which are going to be the individuals that are better in marry mode than all of the people that we saw in date mode. So what we could say is, okay, well, where are they in marry mode? Which marry mode is less than the best that we've ever seen? So best seen in this example is 3. So which lets me know the locations inside of a vector where I find elements that meet a certain logical condition. So where inside the Mary mode vector do I find elements that are less than 3? Well, running this which command, what I end up getting is 3 and 4, indicating that the third and fourth elements of Mary mode are less than 3. And I can confirm that by printing that out to the screen. And so the person that I'm going to propose to is the first one of these. So in this case, there's actually 2 elements of Mary mode that have ranks that are better than who I saw in date mode. I'm going to send that proposal out to this second to last person, the one ranked 2, because that's the first one that I run across who's better than everyone in date mode. So what I can do is I can say, okay, if I look at the minimum of better ranks, that tells me that the third element of Mary mode is the person that I'm going to propose to and marry. So chosen rank is going to be the element that corresponds to where I find min of better ranks. So remember, this is going to be the third element of Mary mode. That was the very first element that had a ranking that was below the best seen, the better ranking here. So I'll extract out that element with the square brackets. So in this case, it lets me know I'm going to marry the person ranked 2. So if we print out chosen rank to the screen here, we can confirm that indeed we end up with a person ranked 2. All right, well, that's one example. It's always useful to run through it just a few more times just to make sure your logic is good before you start, letting it loose inside of a Monte Carlo simulation. So in this case, what I'm going to do is I'm going to switch it up just a little bit. I'm going to switch this 6 and this 3. So here's my date mode. The very first person I run across in Mary mode is the person I'm going to end up marrying because they're better than the 3 individuals in date mode. So chosen rank should be 3 in this case. Yep, looks good. All right, well, one more example, because I haven't tackled the case of, well, what happens when I actually run into rank 1 during my date mode? So why don't I switch this 1 and this 7 here. In this case, I actually run into the most suitable spouse during date mode. I never meet anyone who's better, and so I remain unmarried here. So what's going to happen with the code if I run it with this rank? Well, I get a warning message here, basically because it never found anyone, there's no elements in Mary mode here that has a lower value than 1. And so when I get chosen.rank, I end up getting an NA. So an NA for chosen rank must mean that I remain single. So you'll notice that if I just run this which command, I get an integer 0 back, indicating that, hey, R didn't find anything at all. It's not a number. It's literally a nothing because there are no elements of Mary mode that are less than 1, the best one that we've seen. So a chosen rank of NA must mean, all right, we remain unmarried. This warning message is just letting us know, a helpful error message or warning message, letting us know that, okay, something little anticipated happened during the code, but we understand why this warning is coming up, so we're good with it. So it looks like this logic is pretty airtight, so we can go and start writing a Monte Carlo simulation. So what I'm going to do is I'm going to create a vector to store the chosen rank of the individuals that we marry. So I'm going to say who I marry, and I'm going to left arrow this to be just an empty vector. And I'm going to use a for loop to fill in the elements of who I marry with the chosen ranks as I go from one trial to another. So I'll put in the n trials of 5,000, one of my favorite numbers. And so it's time for the for loop. So just like all of our other Monte Carlo simulations, we set up that for loop. They all kind of look the same with Monte Carlo simulation. For trial in 1 to n trials, the name of my looping variable is just trial here. I'm going to copy and paste this code, and then modify it so that it will play well inside that for loop and accomplish what I want to accomplish. So ranks needs to be chosen randomly. I'm going to come up with a random permutation of the integers 1 through m. Now, in this case, m is 7, and I hard-coded all my examples with just 7 here. But in general, I want to write my code as general as possible. Size equals m, replace equals false. So this will give me a random ordering of the integers 1 through 7. I'll put these up here for good measure. Just to confirm that, run it a few times. Yeah, it looks pretty good. So we get a random shuffling of the numbers 1 through 7 to represent the ranks of the potential spouses that we eventually would run into over the course of our life. We might not see all of them because we might end up married ahead of time before we meet the very last person. We extract out the date mode, the marry mode. These are written in terms of D. I didn't hard code 3, which I used in this example. Then we find the best seen, the better ranks. Chosen rank is what I want to store in who I marry. So I'm going to put a bracket and then trial inside the bracket. Because the first time through the loop, trial is equal to 1, the first element of the looping vector. The second time through the loop, trial is equal to 2, the second element of the looping vector, etc. So we can go ahead and set it loose here. We're going to have a bunch of warnings because these correspond to basically when we came across the overall best mate during date mode, and so it couldn't find any element of marry mode that was better. And so those warnings are a little bit annoying, and you might wonder, okay, well, can we get rid of that? It's good to have code that doesn't have warnings. And let's actually tackle that. Let's take a little diversion before we start studying this to kind of prevent that from happening. So let's go back to this where we run into the best overall potential mate during date mode. And so that way when we say better ranks, we get an integer 0, and that's where we get that warning message. There's no values that are better, so hey, I can't do this. So I can use an if statement here to kind of prevent this warning message from happening. So one thing that I know about integer 0 is that if you ask for the length of that vector, it's going to return 0, because integer 0 literally means emptiness, like there's no elements in it. So if I were to say length better ranks, when there's nothing inside better ranks, when it is an integer 0, I get a 0 back. So what I can do is I can say, well, if length better ranks is greater than 0, then let's have chosen rank be the rank of the person that we end up marrying. I'm going to put this on the second line. Else, we'll have chosen rank just be NA. And so this way, we prevent any sort of warning message. And if we were to replace the code that we had run through before up here, it'll still work just fine. So why don't I go ahead and replace in this for loop here what we just developed. And so this way, when I go through my Monte Carlo simulation, I'm not going to have a whole bunch of warnings that I have to worry about here. So it's all done, we're happy, and now we can get a summary or a table of who I marry. So sometimes I end up with rank 1, sometimes rank 2, 3, and 4. In fact, the most common rank that I end up with is actually rank number 1. That's pretty cool. So let's answer some questions. All right, probability with this strategy of ending up with the best possible mate. So rank number 1. Well, let's use the mean of a logical condition. Let's find the fraction of the elements of who I marry that are equal to 1. Well, that's kind of sad. I get an NA out because all those times that I ended up being single, remember that is what's stored as an NA here. So in this case, what I'm going to do is do the old-fashioned length which to manually count those up instead, because mean isn't really set up to handle NAs all that great. Let's actually do length which, who I marry equals 1. That tells me there's 2112. We got that right there. And we'll divide that by n trials to get the fraction of elements that were equal to 1. So about a 42% chance of ending up with the overall best choice. What about the probability of this strategy of ending up single, never being married? Well, let's do something similar here. We need to check to see, all right, are the values NA? We need to count up the number of NAs. And I'm going to run a command that's not going to work, and I'll explain why it's not going to work. And I'll explain how we do this, how we handle with NAs when we're trying to do arithmetic or counting like this. So if I ask something equivalent like length which, who I marry, is equal to NA, what do I end up getting? I get 0. But that doesn't make any sense because, if I look at the first 10 elements, I see there's NAs there all over the place. So what happened? Well, it turns out that NA is a very special sort of object to R here. You can't just check equality with the double equal sign to see if something is equal or not equal. It turns out there's a whole different code that we need to actually use, a different command, to count this up. So the command here that checks to see if something is NA or not is actually is.na. So if I say is.na, who I marry, I get a bunch of trues and falses. True whenever the object or the element is NA, false when it actually exists. So if I say which is NA, that'll tell me the locations inside that vector where there are NAs. So length which will end up counting up the total number of NAs here. So it looks like there's about a 41% chance that I would end up being married, or being unmarried, being single, and analytics is the only thing keeping me warm at night. So I could also get that the number of NAs, I can read that out, just to confirm that that 2076 is right there. So there we go. So you can rerun this simulation now with your own set of parameters. So let's say you would probably run across 30 potential spouses that you're compatible with over the course of your life, and you decide date mode is going to be, say, 6 people. So you automatically break up with the first 6 people that you would consider potential spouses, and you're going to marry the very next person you come across who's better than those 6 in marry mode. So let's see how well we end up doing. That trial or that simulations run very quickly. What's the probability we end up with mate number 1? About 34%. What's the probability that we end up single and unmarried? About 21% here. So people have studied this mathematically, actually, and there's some pretty interesting results. And I'm going to try to scan and find this result fairly quickly. But here we go. This problem can actually be solved mathematically. So it turns out that as long as M, the number of potential mates you think you'll run across over the course of your life, is fairly large, you can actually choose the optimal value for D, the number of people that should be in date mode. It's just M divided by the number E. So how do you get E and R? It's kind of a funny sounding sentence. EXP, 1 here. You can't take E and raise it to the 1, doesn't know about that. So just take M divided by E, and that is essentially the optimal value for D, the number of people you should have in date mode. And if you employ that strategy, you can show mathematically that the probability you'll end up with mate number 1 is 37%. But I like the Monte Carlo simulation quite a bit better because it allows us to answer much more complicated questions like what's the probability we end up single, what's the probability that we would end up, say, with one of the top 3 mates. We can do stuff like that. In fact, that very last one, why don't we look at the probability with the strategy of ending up with one of the top 3 mates. So same sort of thing, but instead of double checking to see if it's equal to 1 or not, I want to see if it's either 1, 2, or 3. In this case, about a 61% chance. So there you go. In the notes, I talk more about optimizing D, the number that people that you should have in date mode, and then also accounting for, well, what if you don't know what M is ahead of time, your number of mates? What if that's sort of random? You can incorporate that randomness into the Monte Carlo simulation, and you can come up with some pretty powerful statements that if you wanted to use this strategy, what you should be doing.